University, Japan. I appreciate the opportunity to give this presentation. Today, I am going to talk about my research theme, study about assessment of fire safety in a water tunnel by Evacuee's behavior by 3D safety analysis. First of all, I will explain this study's summary. In this study, we simulated evacuations during a fire in a tunnel, especially smoke's behavior by 3D CFD analysis simultaneously with the evacuation simulation. Why do we need to investigate the tunnels? The reason is there are more than 1,600 tunnels longer than 500 meters in Japan. So we have a high possibility of tunnel fire accidents. Therefore, we have to investigate what the tunnel danger is and assess them. And why do we need to study the smoke's behavior by 3D safety analysis? The reason is tunnel spaces are different from buildings. They are large and long. Hence, tunnel fire have some complicated phenomena with regard to smoke's behavior. And we need to consider natural ventilation and traffic jam. Once we have defined the smoke environment level, SE level, made a smoke environment map. And then we made an evacuation behavior map. From this map combined the evacuation simulation because evacuation behavior is ruled by smoke's behavior in a tunnel fire. We then determined the number of people who were surrounded by thick smoke in the simulation. Using this model, we compared 4 cases, different working conditions, that determine when tunnel occupants will stop evacuation. The results are that the tendencies are almost the same, so changing the working conditions was not such an important factor. This slide shows this presentation's contents. I will explain each of them as we go. Japan has a lot of tunnels. This table shows a comparison with the EU. With regard to highway tunnels longer than 500 meters, the EU had 512 tunnels as of 2010. On the other hand, we have 413 tunnels as of 2003, and a total of 1,648 tunnels if you include ordinary national water tunnels. In the EU, managing agencies have to investigate every tunnel over 500 meters to determine whether or not installation of emergency equipment is necessary. In Japan, this equipment must be installed in all tunnels 1,500 meters and longer with high traffic volume. The EU directives inspire reconsidering of the Japanese standard. However, we have a lot of tunnels, so we have to find the best systems which are the most reasonable and effective. First, considering an evacuation in a water tunnel, there are a lot of people along the length of the tunnel who have to evaluate the situation by themselves, decide what to do next, and start the evacuation. Tunnel space is large, long, and enclosed, so evacuation direction is limited to 2 axes. However, one of these axes, the width of the tunnel is so short that we can say almost all the occupant behavior is along one axis. Second, with regarding the smoke's behavior in a water tunnel, the spaces are so unique before said, so tunnel fire have some complicated phenomena with regard to smoke's behavior. There are lamination, smoke descent, and back layering. S is longitudinal slope, and U0 is a longitudinal velocity of a natural ventilation. this direction in a fire start. The right figure shows the smoke distribution of the longitudinal sectional tunnel unit 3. This shows that lamination and smoke descent and back layer. Considering these characteristics with regard to tunnel fires, we need to solve the smoke's behavior in tunnels accurately. Hence, we used Fireless, which is a 3D CFD simulator using various turbulence model and general tool in Japanese road tunnels fire safety. These graphs are comparison Fireless results with experiments of fire in a real tunnel. The length of this tunnel is about 1 kilometer, and this origin is fire point. The left graph shows temperature rise along the ceiling. The right graph shows smoke distribution between the floor and the ceiling. These show CFD of solid liter correspond to experimental results quantitatively. Therefore, present CFD simulation, Fireless, is high quantitative prediction accuracy. And we developed the evacuation simulator. When we had developed this simulator, we remarked the evacuation axis for the reason before said. Therefore, we developed one-dimensional evacuation simulator. The advantages of this simulator are we can get results quickly and average a lot of results. We gave random number, which are dispersion of evacuee's walking speed, passage and rate, and pre-movement time. Hence, we can get a lot of results and process averaging, but not specific data by this simulator. In this study, we used the value of averaging results of 1,000 times with regarding the evacuation simulation. With regarding smoke's behavior, combined evacuation simulation, once we had defined the smoke environment level, SE levels, that consist of smoke density and smoke height from the floor. Next, we developed the smoke environment map using SE levels. About the detail of the SE levels, next slide will show. This slide shows the SE levels. SE level 1 is a situation between that lights cover in thick smoke and thin smoke being ice height. This ice height is human standing. SE level 2 and 3 are situations thin smoke falling down ice height and being thicker. SE level 4 is thick smoke being ice height, and we consider the occupant stop evacuation. SE level 5 to 7 are thick smoke falling down ice height of human landing down. We made a smoke environment map using the SE levels and letting lapse time be the vertical axis and the tunnel length be the horizontal axis. Right figure is a smoke distribution is longitudinal sectional tunnel, and the red figure is smoke environment map. Both conditions are same, which is S equal 1% and U0 is equal 1 meter per sec. With regarding this right figure, top side white line is 4 meters high, and bottom line is 1.5 meters high. 1 minute after fire start, right figure shows that smoke spread along the ceiling and falls below 4 meters high.